What's up, class? So last time we learned about bending stress, or stress and strain, and then bending stress, because that's the one we're going to be dealing with when dealing with a cantilever. Big things to remember about bending stress is that it's not the same throughout the cross section of the member. On top, it's in tension, which is a positive stress. On the bottom, it's compression, which is a negative stress. Okay, you can also think of that as tension is stretching. Once again, this is pushing down. It's going to be stretching like this, and the bottom will be getting pushed together. And we'll kind of see a video of that in a sec. In the middle, at the neutral axis, is 0, and then moment, which is kind of the load that deals with the stress, increases the farther away you are from the load. So at the wall here, we're going to be at our max bending stress because our moment's going to be the highest. Okay, I'm just going to walk through a calculation. You don't have to worry about this. I'm not going to, but this just kind of give you a general idea. So moment is, once again, is force times distance. Y is the distance from the neutral axis, so it's half the height, which is 1.5. The equation for I for rectangles BH cubed over 12. Don't worry about that. But anyways, if you did this, the stress would be 900 pounds per inch squared, or 900 psi. Okay, and that's going to be 900 psi positive on the top and 900 psi negative on the bottom. Okay, this is a video I made from Fusion. It's not the best quality, but it kind of gives you in real time, as the load is increased, how the stress is being distributed. Okay, so this is the largest stress here, and as you get closer and closer to the load, the stress gets closer and closer to 0 until it's 0 right underneath the load, because that's, once again, the moment is 0. And kind of look at the curvature, because that kind of demonstrates the stress, or represents the stress too. And so there's no curvature here, it's straight here, but there's, look at the curvature of the actual cantilever here. So if we pause it, once again, see how the stress is max near the fixed end, and decreases until it's 0 underneath the load. And then I think it's cool to kind of see how it's represented by tension, compression, same yellow, because this is the same magnitude stress. But in the middle, at the neutral axis, it is 0. It is blue. And that's what we talked about before. So we'll watch this one more time. Okay. Cool. And this is what we're going to learn to do in Fusion. Okay, so we're going to calculate real quickly. This just kind of give you another representation of how the stress changes throughout the cross section. Okay, so we're dealing with at the farthest location from the load, so the max tension, max compression. I'm going to calculate it at locations A, B, C, D, and E through the cross section. So this is the top, this is the bottom. So it's like if we cut the beam here and look directly at it like we are here. Okay, C is at the neutral axis. Okay, so Y increases from C. Okay, max 900, then it's 450. At B, C is 0 because it's at the neutral axis. Okay, D is 450, or negative 450 is what it should say, and E is negative 900. Okay, and so once again, this gives you an idea how it goes from max tension on the top to max compression on the bottom. The only thing that's changing, once again, is Y, which is the distance from the neutral axis. The moment's not changing because that deals with the location on the cantilever, not the location in the cross section. And I isn't changing because the moment inertia of the cross section isn't changing. So the only thing that's changing is the distance from the neutral axis. Okay, so we're going to look in more detail. Sorry, I can't speak. In the relationship between stress and strain, and how it kind of works with design. And this is going to be important for our simulation in Fusion.
That the concepts of stress and strain are closely linked. The relationship between the two can be described using a stress-strain diagram. Stress-strain diagrams are different for different materials. We can obtain the diagram for a specific material by performing a tensile test. This involves applying a known force to a test piece and measuring the stress and strain in the test piece as the applied force is increased. Stress-strain diagrams for ductile materials, like this one, show that there is an initial region for low strain values where the relationship between stress and strain is linear. Deformations occurring in this region are fully reversed when the load is removed, and so are said to be elastic. This linear relationship between stress and strain is defined by Hooke's law. The ratio between stress and strain is called Young's modulus, which is an important material property. Hooke's law usually only applies for small strains. For larger strains, the relationship between stress and strain is no longer linear. Deformations are not reversed when the load is removed, and we have permanent plastic deformation.
Okay, I'm going to watch one more video. This actually has, along with the curve, the stretching of a metal rod, so kind of gives you another way to look at it.
Let's do a small experiment to understand the stress-strain curve. You see this thin steel wire? Let's see how its deformation happens. On the right, you can see the stress versus strain curve of the steel wire. Now, when the steel wire is under continuous tensile stress, as expected, it elongates. Now look at the graph. The elongation is linearly proportional to the applied stress. So this region in the graph is what it is. If the stress, that is the load, is released, what will happen? See there, the steel wire gets back to its original length. Now within this stress limit, the steel wire follows Hooke's law. What it means is the deformation is elastic. Now let's increase the load further. And what do we see? After a certain point, look at the graph. The wire is not following Hooke's law. That is, stress is no longer proportional to the strain. But if you release the stress, the wire still goes back to its original length. The limit of this behavior in stress-strain curve, that is this point, is known as the yield point. Now, if we increase the stress further, the strain will also increase, no doubt, but it will not follow Hooke's law. What it means is, even if there is a very small increase in stress, the deformation will be much more, and the wire will not return to its original length, even after we release the stress. So in this range, we can say that the deformation is plastic. And what happens? You increase the stress further, as expected, the wire will ultimately break. And that is the breaking point.
Okay, so kind of just want to go over what I kind of want you to get out of it. When we're dealing with design, we're dealing with this part of the stress strain curve, which is the elastic portion. Okay, it's before it yields. Okay, and what does that mean? It means a couple of things. First, we know that when we put a stress on it, we're going to get a certain reaction from it. So there's a constant change in strain compared to the change in stress. So that's called Young's modulus. Okay, and that's a linear relationship. And that's really important when we're dealing with design. That we know when we put this much stress, we're going to get this reaction from it. Once we get past the yield, we kind of lose that. Okay. Also, what's important about the yield is before that, if we reduce the load or let go of the load, it's going to go back to where it started. So it's elastic in this part. It's kind of like a rubber band. Okay. So once again, if you let go of it before the yield, there will be no permanent deformation, which is huge, obviously, in design, because you don't want permanent deformation in your structural members. Okay, and then ultimate strength is important because that's obviously where it breaks. Though it continues to strain after this, if you increase the load, obviously it's going to break, or if you keep the load the same, obviously it's going to break. So this is the point where if you get to this load, you're in trouble. Okay, so those are the two big things. Once again, the elastic modulus, which is change in strain over the change in stress before yield, and then the yield strength and ultimate strength. Another way I like to look at this is like if you're messing around with a piece of plastic. I think back to when I was bored in school and I would have a mechanical pencil with a plastic clip and I would bend it back and forth. And at first with low load, low force, it would just go back to normal. But if I bent it too much, it would turn white and be permanently deformed. So that's past the yield. And if I bent it too much past that, it would break. Okay. So real quickly, we're going to talk about deflection. Okay. You don't need to know this in detail, but I just want the equation, which is PL cubed over 3EI. If we calculate it with this example, the elastic modulus for steel is 29 times 10 to the 6 psi. Okay. This example we've had before, and with that load, we would get deflection of 0.0089 inches. Okay. But once again, the big thing I want you to get from this is this relationship. So if we go back to our goal is for the skyscraper to act as a single cantilever that's experiencing minimum stress and deflection while reducing material cost. So let's look at the two main equations: bending stress, which is my over I, and deflection, which is PL cubed over 3EI. Okay, all these variables, m, y, p, l, and e, are constant. If you think about it, m and p deal with the wind load, y deals with the cross section size, so that's like actual like block to block radius of the building, okay, which isn't changing. L is the height, so you want that actually as tall as possible, right? Which is part of the issue. You can see kind of how, kind of going back to our point that the taller it is, the more flexible it is with the cubed here. Then E deals with the material properties. So all those things are kind of constant. The one thing we can control in our design is I, okay, which is the moment of inertia. So we want the largest moment of inertia, I, that has the lowest mass possible. So about how we can do that. Okay, but to understand that, you need to understand how it's calculated. Basically, it's the mass of the cross section times its distance from the center of mass. Okay, and you square that distance. So this R is huge. So the bigger this R is, the more effect you're going to have on the moment of inertia, which we want larger, right? Because if you go back to our equations, the larger I is, the less stress and the less deflection we're going to have, okay? So we got to move that mass basically as far away from the center of mass as possible, okay? If you look at kind of light poles or traffic lights, okay, and you look at those actual poles, they're going to be hollow. Why is that? It's because that material in the middle, its distance from the center of mass is less than the outer material, so it's kind of not useful, okay, in terms of cost, okay? So we'll kind of look at that more in detail, but with this in mind, Fazlakhan came up with a tube structural system where skyscrapers will act as a hollow tube cantilever coming out of the ground. Okay, so once again, the equation is like the sum of the mass times R squared. Okay, so obviously the strongest one would be with not a hollow middle and material all the way through, okay? But if you think about it, that's a lot of wasted material. So the tube structural system increases moment of inertia while saving a lot of material cost. Material that is close to the center of mass is not necessary because it does not have a large enough effect on the moment of inertia. That's because its R is so much smaller than the material on the outside, okay? So this is kind of unnecessary material, and so you get rid of that, and you're left with this tube system, okay? So that's the end of this video. Moving forward, we're going to talk about how we take this tube structural system and how we apply it to actual buildings and how we actually was able to have buildings behave like this.